Hi students, it's Dr. Marks, and we're still talking about inferential statistics, but we're moving on to talk about hypothesis testing, something that's really useful. We have to do this in parts. For this lecture, we're simply trying to set up the idea of a hypothesis test, but we have to understand, is something going to be one-tailed or two-tailed? So that's where we're going to start. Now, as we've already said, we're still talking about inferential statistics in this part of the course. And we've done some of this already, right? We've looked at confidence intervals, and that was inferential statistics. But we might also want to test hypotheses. For example, is the mean salary of women significantly different from the mean salary of men? Or is mean grades of MBA students higher for those who are working versus not working? Well, we could use hypothesis testing to help answer that question. And finally, does mean blood pressure differ when I'm comparing accountants to doctors, right? Both can be stressful jobs. Would I expect any difference there? Let's use as our example the question of, does smoking impact lifespan? Now, we have a pretty good idea that it does, right? In modern society, it would be hard to think otherwise. But if I wanted to do this statistically, I would need to look at the population of smokers and take a sample, and look at the population of non-smokers and take a sample from that population as well. Then I conduct a statistical test to see if lifespan is indeed different. Now, we can infer things based on the properties of the normal distribution, and we're going to be relying on that when we do hypothesis testing. Remember that thing, the t-distribution, which we've already talked about? Well, that was also a bell-shaped distribution, and it was one that helps us with smaller samples. But we know it approaches the normal distribution when our samples are large enough, and we talked about greater than 30. And remember, why do we care about that? Because the normal distribution has these properties that we know and we understand and we can rely on. So we can use the t-distribution, which converges to the normal distribution in our hypothesis tests. Let's say we have our two samples and we determine that the mean age at death is 71.3 for smokers and it's 76.8 for non-smokers. And we see that it's different, right? I'm not trying to say it's identical. I can see that I get a different mean age, but that's not exactly what we're trying to do here. What we're trying to do is test to see if there's a statistical difference. And by statistical difference, we are saying, look, this is not due to chance. It doesn't happen to be that given my samples of smokers and my samples of non-smokers that I get this result. To do this, I need to create a hypothesis test. And maybe I think that smokers have statistically significantly different ages at death, but maybe they don't, right? So our hypothesis test is going to tell us what's in fact true based on the evidence. Now, first, we have to decide if this is going to be a one-tailed or a two-tailed test. And it's going to turn out it depends on your expectations. In other words, do you think one mean is higher than the other or not? For example, maybe you think that non-smokers' age at death, again, we're talking about the mean, is greater than smokers' mean age at death. Well, it seems like that would be a reasonable expectation. But maybe you just want to know if means are different, and you don't have any expectation at all going into the investigation. For example, do females and males perform differently on a specific test? You don't know if males perform better than females, or females perform better than males, or maybe it turns out there's no difference at all. Why is it that we need to understand one-tailed versus two-tailed? Why does it even matter? Well, for one, it changes the way we write the hypothesis test. And it also changes what we're testing. We're going to see that the bar that we use will be different. And by bar, I mean the bar you have to clear to say, oh, this is a statistical difference, or not. So what I'm saying is that we're going to have slightly different standards when we're doing one-tailed tests versus two-tailed tests. And we're going to cover this pretty thoroughly, so more on that later. Just tuck that away for now. When we talk about one-tailed tests, we might also be calling it a directional hypothesis. Again, you come at it with a certain expectation. In other words, you expect one mean to be greater than the other mean, of course, in the case of comparing means. An example might be mean weight for men versus mean weight for women. If I took a sample of weights for men and a sample of weights for women, it might be reasonable to expect that the mean weight for men would be greater than the mean weight for women. After all, men are on average taller. Or another example, if I'm looking at housing prices in New York versus housing prices in Kentucky, it would be reasonable to assume that the mean house price in New York is greater than the mean house price in Kentucky. So I come at it with an expectation. Now, that doesn't guarantee it's true, but I'm coming with an expectation. In other words, I'm coming with a directional hypothesis. For two-tailed tests, however, there's no direction involved. So think of this more as exploratory. You just want to know if the means are different. So maybe you have reason to believe means are different, but you don't really know if one mean is going to be bigger or smaller than the other. For example, do men or women have higher mean grades in this particular class, right? My MBA class. Well, I don't have any idea if men or women are going to have higher mean performance. So this is not directional, right? It's purely exploratory. We can see that we would frame a one-tailed hypothesis different than a two-tailed hypothesis. For the one-tailed, I might be saying, hey, I'm coming in with the expectation that males score higher on math tests than females, so I'm testing that specifically. But a two-tailed test would simply say, hey, do males and females perform differently on math tests? I don't know. I don't know which one would perform higher. And maybe they don't perform differently at all. In a second example, my one-tailed test, I might say, hey, I think female managers are paid more than male managers. And I come in with that expectation. But if I really have a two-tailed hypothesis and I'm saying, hey, do female and male managers get paid differently or not? Finally, does joining a fraternity decrease GPAs? Well, maybe my hypothesis is I think joining a fraternity decreases GPAs. And if I come in with that expectation, then I have a one-tailed test. But maybe you can come up with arguments where joining a fraternity would increase GPA or decrease GPA. And if that's the case, then you don't have a directional hypothesis. This is a two-tailed test. For example, I have two children that went to University of Virginia, and they both joined a fraternity, the same one, and there was a lot of partying. So I might say to myself, wow, maybe joining a fraternity with all the partying and beer, maybe GPAs are going to go down. But at the same time, I might say, look, my son has all these friends and they're really smart, and this is a high GPA fraternity, and they help each other and they study together, and maybe that's actually increased his GPA. Could be. So then I'd have to be thinking about a two-tailed test. Let's see if you can determine if these are one-tailed or two-tailed. You hypothesize that people who exercise have lower cholesterol than those who do not. So if that's your hypothesis, would this be one-tailed or two-tailed? It would be one-tailed. You think that school systems in rural counties have lower test scores than those in suburbs. If that's what you're interested in testing, agree, it's one-tailed. You want to determine if students working part-time in college earn higher or lower GPAs. You don't know. Everyone agree? That's two-tailed. Now, we'll talk more about this later, but you would only have a one-tailed hypothesis if you had a really good reason to. If you can tell competing stories or you're just not sure, there's not really compelling evidence or information out there, then you're probably talking about a two-tailed test. So back to our smokers and our non-smokers. Would this be a one-tailed or a two-tailed test? Well, everyone agree it's going to be a one-tailed test. And the reason is that research seems to support that death is at a younger age for smokers. And again, we're not saying for every single smoker, we're saying mean, if I take a large sample and calculate the mean. In other words, we think non-smokers on average live longer. So, seems like that would be reasonable to run as a one-tailed test. Now, there's different ways to write our hypothesis. And I'm not saying that this is our hypothesis test written out. I just want to show you that we can write this in a few different ways. We could say, hey, look, I think the mean age at death for smokers is less than the mean age for non-smokers. All right, that's one way. Or I can just subtract one from the other. The mean age for smokers minus the mean age for non-smokers, since I think the bigger number is smaller and the second number is bigger, that's going to give me a negative, right? So I can look at the difference and say the difference is negative. Or I can just flip A, right, in a sense, and say, look, or flip B rather, I guess it is, take the mean age of non-smokers, which is higher, subtract the mean age for my smokers. I think that the first number is bigger than the second number, so that's difference is going to be greater than 0. These are all three different ways to write the same thing. So I'm throwing this out there just so I don't confuse anyone. When you see stuff, it could be written slightly differently. Let's talk about actually stating our hypotheses. Well, let's set up a hypothesis test, and it's going to turn out there's two parts to our hypothesis test. We're going to start with a null hypothesis, and that's the thing we don't think is true. The thing we don't like is true. And I'm simplifying this just a little bit. So the null hypothesis we see has H with the subscript 0, the thing we don't think is true. Then our alternate hypothesis, H subscript A, is the thing that we do think is true. That's our combination. So our hypothesis test really is two different statements, but they have to be mutually exclusive, right? Something can't meet both the first and the second part of that hypothesis. Now, when we subject this hypothesis test to an actual statistical test, I only have two options. When I'm done, I have to say that either I reject the null, or we might call that H naught, we reject the null, or we fail to reject the null. Those are the only two options. And I want you to be very clear, because it would be very imprecise to say something like, we accept the null. That's not good statistical language. Or we reject the alternative hypothesis. Not good either. So you only have two options, reject the null or fail to reject the null. And it depends on how much evidence there is against the null. If there's strong evidence against the null, then we're going to reject the null. But if there's not strong evidence against the null, then all we can say is we fail to reject the null. There's just not enough evidence to reject the null. So we reject the null or we fail to reject the null. So what would our hypothesis test look like for this example, which we've already said is a one-tailed test? Well, our null hypothesis, and again, there's different ways to write it, but make sure this one makes sense. Remember, this is the thing we don't think is true. Remember, we think that the mean age at death for non-smokers is greater than smokers. So if I take the age at death for smokers minus that mean for non-smokers, I really think it's going to be negative, right? I think that smokers is smaller than non-smokers. But remember, the hypothesis for my null hypothesis is the opposite of what I think. That's why it has to be greater than or equal to 0. The equal part says they're the same mean age at death. I don't think that. And the greater than part says that smokers live longer than non-smokers. I don't believe that either. So do you see why both of those things have to go into my null hypothesis, the thing I don't think is true? That leaves me with our alternate hypothesis, which is that mean age at death for smokers minus our mean age at death for our non-smokers. Well, I think that smokers die earlier, so the first number is smaller than the second number. When I take mean smokers minus the mean for non-smokers, that should be a negative number. That's why I have less than 0. So remember, our null hypothesis captures those things that we don't think are true, and our alternate hypothesis captures the things that we do think is true. But I could write it backwards. It doesn't matter. I could go back to that previous slide where we said, look, you could have mean of non-smokers greater than smokers, right? We could just reverse the order. But if I reverse the order, then I have to reverse the inequality, right? So I'm not trying to confuse you there. I just want to point that out. Let's look at another example. Maybe I'm looking at newly minted PhDs in finance and accounting and their new hires, and I want to know if they have statistically different mean salaries. Now, I see from my sample that they're different, but that's not the same thing as saying they're statistically different. Maybe this is just by chance, given the samples that I've collected. So we want to see if they're statistically different, that it's not just simply due to chance. So let's suppose that this study is exploratory, and by that I mean I don't have an expectation about who is paid more. So I'm going in just saying, hey, I want the hypothesis test to tell me if they're different or not. So let the data tell me if there's even a statistically significant difference or not. So would this be one-tailed or two-tailed? Well, I'm guessing you already understand this, that this would be two-tailed because it's not a directional hypothesis. I'm coming in simply exploratory with my logic, right? So let's write out our hypothesis test for a two-tailed test. Well, it turns out that the hypothesis test is a lot simpler when it's a non-directional test or two-tailed test. My null hypothesis is simply that the means are equal. And my alternate hypothesis is that the means are not equal, right? So my null captures the idea that there's no difference, and my alternate hypothesis here captures the idea that there is a difference. Now, again, for the two-tailed test, saying that the null captures the thing that isn't true, that doesn't quite work here. But you get the idea. No difference is going to be our null. Difference is going to be our alternative hypothesis. All right? Now, let's compare the one-tailed and the two-tailed test side by side so we can simply see the difference. Do you agree that the only difference is in the inequalities, right? The two-tailed test is easy because it's either they're equal or they're not equal. The means are equal, mean 1 and 2, or they're not equal. So on the right, that's why we just have the equal and the not equal sign. But on the left, with our one-tailed test, because they are directional, I have to put in my alternate hypothesis. Remember, H sub A, my alternate hypothesis captures the thing that I think is true. So in this case, I'm saying, hey, I think mean 1 is greater than mean 2, and that's why I have the greater than sign. But everything else goes in my null. That's why my null has to be not just less than, but the equal, because I don't think the means are equal either. So that's a really important point, that equal sign has to go somewhere. Make sure that you understand the one-tailed versus the two-tailed test. Clearly the two-tailed's just a little bit easier, right? And again, let me remind you that you're going to see that the bar is different when we look at trying to clear the bar for a one-tailed test versus a two-tailed test to determine that there is statistical significance. You really only want to use a one-tailed test when there's some real reason If you're kind of grasping at straws or you kind of think, but there's really no logic behind what you're thinking, you should probably be using the one-tailed test. With our smoking example, I don't think anyone is going to argue that smokers outlive non-smokers, so I don't think anyone's going to give you a hard time for using a one-tailed test. And if you used a two-tailed test, somebody might go, well, shouldn't that really be a one-tailed test? Because it's unlikely that smokers outlive non-smokers. It seems like this really only works in one direction. Quickly, just remind yourself that we could write this in the other direction, right? Mean 1 minus mean 2 being greater than 0 is the same thing as saying mean 2 minus mean 1 is less than 0. So I don't want to confuse you there. We can also write our hypotheses slightly differently. These are the same mathematical expressions. I just want you to take a quick look and make sure you see that these are indeed the same. That if I give you the ones on the top, they are the same as the ones on the bottom. So just inspect this for one moment and make sure that you agree with me that these are all identical, right? Whether I'm using the difference approach, so in the top, I'm using a difference approach, mean 1 minus mean 2, and in the bottom, I'm not. But they are the same. Let's move on to talk about testing significance, right? So to test our hypothesis, we're going to use a t-test. Now, I'm guessing that way back in the recesses of your brain, for those of you that haven't had statistics for a long time, that probably when I said t-test, you were like, oh, wait, I vaguely remember something about that. All right, I guarantee you all did t-tests in your stat class. You did it using that t-distribution, right? We have this t-distribution we've learned a little bit about. Remember, our t-distribution is going to give us the probability that the difference in means that we observe was due to chance. So we're trying to get a sense of, hey, is there a real difference, a statistical difference, or is it really just a difference that's due to chance? So this ties into this t-distribution that we're going to learn how to use. Remember, that t-distribution is also a bell-shaped distribution, but the t-distribution converges to a normal distribution when we have large n, right? We talked about over 30. And so this t-distribution converging to a normal distribution is really useful for us. Remember, we've already talked a few times about the fact that we understand normal distributions. They have certain properties that we can rely on, and that's going to give us some mileage here. So this will be only somewhat clear to you, but I want to kind of set up where we're going. If we're talking about a two-tailed test, then the probability that this is due to chance exists in both tails, like in picture A. And I'm keeping this overly simple. But a one-tailed test has probability that our outcome was simply due to chance, but only in one of the tails, either B or C, depending on which direction our hypothesis is, right? Depends on which mean we think is bigger, how we express it. So we need to understand how to use the t-distribution as it corresponds to the type of hypothesis that we're testing. So while I don't expect you to understand these areas in the tails yet, I do want you to understand that where we look in our t-distribution depends on if I need to look at both tails, like in A, like in a two-tailed test, or if I need to look in only one tail, like B or C, corresponding to a one-tailed test. So that idea should make some sense. But we're going to clearly be firming this up, not in this lecture though. The t-distribution shows us the region where we fail to reject H naught, our null hypothesis, right? So there's some probability that we fail to reject H naught. And that's going to come from an area in our t-distribution. But this region depends on degrees of freedom. So we have to revisit this idea of degrees of freedom, something that we brought up in this class a while ago. Degrees of freedom depends on n, our number of observations. So when we're using our t-table to figure out the chance of failing to reject H naught, well, it's going to depend on our degrees of freedom, which depends on our number of observations. There's not just kind of one number to go look at. This means we have to learn how to use the t-distribution for different degrees of freedom that come from different numbers of observations. Now, we're going to be focusing on difference in means specifically. That's what I've been talking about this whole time, that I'm testing to see if my means are different. Of course, assuming independent samples, that my sample that I took from, first is independent of my sample I took second. But I want you to understand that there are other hypotheses that we could test in a very similar manner, meaning that if you understand this, you understand how to do other tests. For example, we could test for differences in proportions or percentages. It doesn't have to be just a mean. Maybe I'm interested to see if the proportion of female Longwood students who are out of state compares to, is higher or less than, the proportion of male Longwood students who are out of state, right? It turns out that it works similarly. So if you learn how to do a simple hypothesis test for differences in means, then you'll be able to do a hypothesis test for differences in proportions because it works similarly. Now, in our next lecture, we're going to learn how to conduct the hypothesis test. For this lecture, the key takeaways that you need to make sure you understand before moving on is one-tailed versus two-tailed test and how to set up a hypothesis test given one-tailed or two-tailed tests. That is going to be very important as we learn how to actually conduct the hypothesis tests themselves. So please let me know if you have any questions. Thank you so much for listening and have a fantastic day.